All right, so in this chapter, what we're doing is studying fixed axis rotation. So a rigid object rotating about a fixed axis. Okay, so for instance, here's an object, and now these guys actually turn into the wind, but we'll assume that the axis of rotation, which is that, is fixed. And this is a rigid object that rotates about that fixed axis, and that's what we're going to describe. We learned all of this last time. And the reason we're talking about this is because every point on this object rotates through the same angle. Okay? And so that's a simple object. That's a motion that's easy to describe. Okay? So this is, as you learned, very similar to an object traveling in a straight line. Okay? And this was easy to describe because every point on this object had the same velocity, same displacement, same acceleration. And similarly, you'll have the same situation here. So let me show you a crazy motion. Okay, so let's say this is, again, this is an artificial motion. So let's say it goes like that and all that kind of stuff. It rotates. Okay, so the rotation of that motion can be described by giving this function, theta as a function of time. Okay. And what are you doing to measure theta? You'll have a reference axis. So let's say this is a reference axis. You mark a point on the object, and this will be the theta that you measure. Okay. So you learned that last time. Okay. And so let's say this is a motion that somebody gave you. So let's do it here. Theta t is 7t cubed plus 8t squared plus 9t plus 10. Okay, and okay, so we want to generally give the angle in radians, but you can give in revolutions, degrees, or whatever units you want to choose. Okay, so here's a motion that is described, and you saw that its angular velocity, denoted by omega, is the time derivative of that. Okay, so 21 t squared plus 16t plus 9, and the units would be radians per second. Radians for this guy, seconds for this guy. So radians per second. And if you wanted to calculate angular acceleration, alpha theta would be d omega by dt, time derivative of the angular velocity with respect to time. Okay, time derivative of the angular velocity, or the second time derivative of the angular position, which would be 42t plus 16, and the units would be radians per second squared. Okay, so that's what this chapter is about. Okay. You want to describe the motion of a rigid object rotating about a fixed axis, which is given by that. Here's the angular velocity as a function of time. Here's the angular acceleration. Okay, and generally that's what we're interested in. Okay, so that's what we were studying. All right. So again, so here's this object. There's your reference line. Okay, and we'll mark a point on the object, and whatever angle that point rotates through, every point on the object rotates through the same angle. Okay, so let's say this was the initial position. It's rotating counterclockwise, and that point travels a distance, linear distance s. The angle through which this object has rotated, theta, is s divided by r. Theta is in radians there. So now the disk is not drawn, so that's the initial position of the disk, and there's the final position of the disk, and there's the angular displacement. Okay. We saw all of that. So angular velocity, denoted by omega, is d theta by dt. Okay. I'm just giving you guys a review of what we talked about. Okay. Now, for linear motion in one dimension, Okay, so the object is confined to move in one dimension. The velocity can either point to the right or to the left. Velocities are vectors. Okay, and so we took these velocities to be positive. Okay, so if that's the positive direction, so this velocity was plus 5 meters per second, and this guy was, let's say, negative 6 meters per second. Okay, so you see, in one dimension, the direction was given by the sign. The sign indicated the direction of the vector. You didn't need a number to give you the direction. Just like that, rotation about a fixed axis, the direction of the velocity is given by this right-hand rule. The direction of the velocity points along the axis. And there's only one of two ways you can point, either this way or that way. Okay? And when the object is rotating counterclockwise, that is taken to be positive, just like right is taken to be positive. That's just a convention. Okay? And this velocity is negative. Okay. Angular acceleration. Angular acceleration is time rate of change of angular velocity. Okay. So if the angular velocity of this object is changing, then it has angular acceleration. Okay. You saw that for the linear case, if the acceleration vector is pointing in the same direction as the velocity vector, then the object is speeding up. If the acceleration vector is pointing in the opposite direction of the velocity, then the object is slowing down. Okay? So similarly, if the angular acceleration is pointing in the same direction as angular velocity, the object is speeding up, so it's spinning faster and faster. If the angular acceleration is pointing in the opposite direction of the velocity, angular velocity, then it's slowing down. So the object is spinning in that direction, except that the spin rate is decreasing. Okay, it's slowing down. So that's what this shows you. All right. Now, if so, here's, let's say, here's a disk that is spinning. Okay, and if it's spinning faster and faster, if it has angular acceleration, what this tells you is a point whose position is given by the r from the axis of rotation. If it has angular acceleration, this point has tangential acceleration. Its speed is changing. Okay, it's instantaneous velocity. The direction is also changing, but the magnitude of the velocity is changing. And the rate of change of speed of that point is given by that. Okay, so the tangential acceleration is angular acceleration cross r. Okay, it's this vector crossed with this vector. It gives you the tangential acceleration in that direction. Okay, and that point is going in a circle, so it's also called tangential acceleration because the acceleration is tangent to the path. All right, then we wanted to specifically study when acceleration was constant. Okay, when acceleration is constant, this formula gives you the angular velocity as a function of time. So the angular velocity is a linear function of time. So when alpha is constant, angular velocity increases linearly with time. This formula shows you when angular acceleration is constant, okay, this gives you the angular displacement, or you can also think of this as it's giving you the position. Theta as a function of time, it's a quadratic function of time. Okay, so the angular position is a quadratic function of time. Okay. This is giving you the angular velocity as a function of displacement. Okay, if you have constant angular acceleration, let's say this is positive acceleration, the more you have rotated, the faster you're going. That's what it's telling you. Okay. All right, so this is giving you angular velocity as a function of position. Okay. This is giving you angular velocity as a function of time. This is giving you angular velocity as a function of angular position. It's like, and these guys are, so for constant acceleration, for constant linear acceleration, there are the equations of motion. Those are the kinetic kinematics equations, giving you velocity and function and position as a function of time. For constant acceleration, here, angular acceleration, here the kinematic equation giving you velocity and position as a function of time. Okay. From these equations, you can get all these equations by this simple replacement. If you replace x by theta, v by omega, a by alpha, for all these equations, you'll get the corresponding equation. Okay. All right, so rotational motion about a fixed axis, rotational motion of a rigid object about a fixed axis is very similar to linear motion. Okay. All right, so when this object is rotating, so the axis is coming out of the sheet. When this object is rotating, okay, the faster it's rotating, the faster this point is going around in a circle. The speed of this particle is related to the angular velocity, like so. The further you are from the axis, the bigger the circle you have to make and the faster you have to go. Okay, so the speed is r is the distance from the axis of rotation, and omega is the angular velocity. Okay. Now, whenever you see a formula that relates linear quantities to angular quantities, this has to be in radians per second. Okay, the units for the angles have to be in radians. Okay, so you will see formulas. R is S, the linear distance that it has traveled, the linear distance that the point has traveled is R times theta. Okay, so theta is in radians there. V is R times omega, and tangential acceleration is R times alpha. Okay, so these are the three formulas that you'll see that are relating linear quantities to angular quantities. And in all these formulas, these guys are in radians, radians per second squared. Okay. Okay, so there's the tangential acceleration is R times alpha. All right, so when this object rotating about that axis has angular acceleration, the speed of this guy is changing, but the direction of that point, the direction of the velocity of that point is changing. So it has centripetal acceleration as well, or radial acceleration. Okay, so it has tangential acceleration and centripetal acceleration. The tangential acceleration is given by r alpha. R is the distance from the axis of rotation, is given by r alpha. And the instantaneous centripetal acceleration is given by the instantaneous speed squared divided by r. So it has, this point has two accelerations when the object has angular acceleration. It has tangential acceleration and centripetal acceleration. Okay. If it doesn't have angular acceleration, if alpha is 0, the tangential acceleration will be 0, meaning its speed is not changing. But it will still have centripetal acceleration because the direction of the velocity is changing. Okay. So you have to be careful about that. Okay, we saw this last time when an object is rotating. It has kinetic energy. Kinetic energy is the energy in the motion of the object. Okay, so here was for an object with linear motion. This was the formula for kinetic energy, 1/2 mv squared. The problem here is that every particle is moving with a different velocity, with a different speed. Okay, so the further out you are, the faster you're moving. Okay. So what we found is what is the same is the angular speed is the same for all objects, for all points. Okay. So we wanted to express kinetic energy in terms of angular speed. And what we find is then mass gets replaced by moment of inertia. Okay, so the parallel formula for kinetic energy is 1/2 I omega squared. Velocity gets replaced by angular velocity and mass gets replaced by moment of inertia. And the moment of inertia of an object depends on the mass of the object and how far that mass is from the axis of rotation. So for this object, you can break it up into little pieces. Okay. So these are the MI. So the moment of inertia depends on the mass of the object and how far that mass is located from the axis of rotation. So you can take the same object and distribute its mass further from the axis of rotation and its moment of inertia increases. So for instance, you've seen this in an ice skater. All right. So I'll show this to you. So this is the conservation of angular momentum. Okay, so I can rotate about this axis. Okay. My mass is not changing. My mass is the same, but I can change the distribution of the mass about the axis. Okay. Now I've increased my moment of inertia, and now I've decreased my moment of inertia. Okay. So, just like, so by the way, for the recording people, I'm sitting on a chair and trying to spin. Okay. So here we go. So if this was a frictionless system, my total angular momentum is conserved. Okay. So you can change your moment of inertia by changing the distribution of the mass about the axis of rotation. Okay. So you will learn that what I just showed you was L is the angular momentum, which is I times omega. When I decrease my moment of inertia, my angular velocity increased. Okay. Again, we'll talk about this in the next chapter. And that's what a ice skater does. When he or she brings their arms in, they're decreasing their moment of inertia and increasing their angular velocity. All right, so the kinetic energy of rotation is 1/2 I omega squared. Okay, and the moment of inertia depends on the mass and how the mass is distributed about the axis of rotation. Okay. So a given object can have infinitely many moments of inertia. The moment of inertia will depend on the choice of axis about which you're calculating the moment of inertia. Okay. So for instance, here's this object. If you calculate the moment of inertia about this axis, there's the moment of inertia. For the same object, if you calculate the moment of inertia about this axis, there's the moment of inertia. Okay, so later in this chapter, you'll see that moment, if you apply a torque to an object, the angular acceleration is I times alpha. So to give this object an angular acceleration about this axis is harder because moment of inertia is greater. You need a greater torque to give the same angular acceleration. Okay? So it's easier to spin this object about this axis than this axis. Okay? All right. Now the moment of inertia is an important enough quantity where they give you tables. So to calculate the moment of inertia of a continuous object, it's a triple integral. Okay, and people have done these triple integrals for you guys. So there's the moment of inertia of this of a ring about that axis. Okay, again, moments of inertia are given about particular axes. Okay. The most commonly used axes. Okay, so the moment of inertia of this cylinder is about that axis, about that axis. The moment of inertia of a solid sphere is 2/5 mr squared, and so on. Okay, In general, the further the mass is distributed from the axis of rotation, the greater the moment of inertia. Okay. So generally in tables, they give you moments of inertia that pass through the center of mass axis. Okay. Or it doesn't matter, so whatever the table gives, but that's generally what's given. So let's say you have the moment of inertia about one axis. Okay. You can calculate the moment of inertia about another axis using this theorem. Okay. So the moment of inertia about this axis is the moment of inertia about this axis plus the mass of this entire object divided by d squared. Okay. Now this is given about the center of mass, but you can apply this to, if you know the moment of inertia about this axis, then you can calculate about that axis as well. Okay.
You said that's distance squared? Or
Yeah, that's d is this distance.
I think we also. Yeah, so for like the table,
Mm.
like that, would those values typically be given, or should we write out something like that on our sheet?
Yeah, you can write it down if you want, but if you haven't written it down, I can give it to you. Yep. Yep. All right. We saw that forces give you linear acceleration. And what we learned is something called torque gives you angular acceleration. Okay, so torques take the job of forces for linear motion. Okay. Now let me show you something. All right. So let's say we are on an air hockey table. Okay. So this is a top view. Okay. And I have a bar here, and there's the center of mass of the bar. Okay. So we are taking a top view. Now if I push this object, if I give this object a force, what will happen? So this is the center of mass, and I push this object at that point. What will happen, you think? I'm sorry?
All points will move at equal speed.
Right, so it'll accelerate. So as long as you keep pushing it, it'll accelerate in that direction. Now let me do the following. Okay, there's the center of mass. Again, I'm going to apply the same force. What will happen now?
The outside will accelerate faster than the inside.
That's right. So it will have linear acceleration and it will spin as well. It will have angular acceleration as well. Okay? So, all right, now we'll do a third experiment. Okay, so we'll do it again, except that this time we'll apply the force there. Now what will happen?
It'll spin even faster.
It'll spin faster. Okay, so forces can give you linear acceleration and angular acceleration. The effectiveness of a force in giving you angular acceleration depends on something called the torque, which depends on how large the force is and the moment arm. The moment arm is that perpendicular distance. Okay? So the effectiveness of a force in giving an object rotational motion, forces can cause linear motion and rotational motion. Okay? What do torques measure? The efficacy of a force in causing rotational motion depends on its moment arm as well as the magnitude of the force. Greater the moment arm, greater the torque. Okay? And that is, okay, so torque is defined as the magnitude of the force times the moment arm. Okay? And what is this moment arm? So if this is the force and you're calculating the force about that point, this perpendicular distance is the moment arm. Okay. So for instance, for this guy, you're calculating the force about that point, there's the moment arm. There's the moment arm. For this guy, there's the line of action of the force, and there's the moment arm. Okay. So, for instance, if I apply that force to the door at that point, how large a force would I need to rotate that to open the door? I'm sorry? I'm sorry? Well, you couldn't open the door. The torque would be zero. The moment arm is zero. And an infinite force as well won't open the door. You might pull it out of the hinge, but that's a different story. Okay? So for this case, the moment arm was zero and the torque was zero. Okay? All right, so here is the general definition of torque. Torque can be calculated about any point if this is the force. R is the vector from the point about which you're calculating the torque. There's the vector, and the torque is R cross F. Okay, and in this case, so here's a good way to think about this. This force can be broken up into two components. Here's the perpendicular component, and here's the parallel component. And this force is going through the axis. This force will have zero torque. Only this force will have a torque. And the magnitude of the torque will be this force times R. So the magnitude of the torque will be the perpendicular force times R. Okay. All right. Now in this slide, what is being shown is, okay, what is Newton's second law for linear motion? Do you guys remember Newton's second law? What's Newton's second law? I'm sorry? F equals ma. So F equals ma. When was this true? This is not the most general form. This is the general form. Okay. This is the general form of Newton's second law. When was this true? When mass was constant. Okay. So similarly, we will learn that the parallel of Newton's second law for rotational motion is the general form is dl by dt. What is L? L is angular momentum, just like this was linear momentum. Okay. And this was when mass was constant. Just like that. This, when I is constant, I is the parallel of mass, remember? When I is constant, then torque will be I times alpha. Okay. So this is the special case for when moment of inertia is constant. I showed you a case when moment of inertia is changing. Now I sit on this chair and redistribute my mass, and my moment of inertia was changing. Okay? So in that case, this formula would not apply when the moment of inertia was changing. Okay? Okay, that's what this derivation shows you. Okay? Torque is I times alpha for the case when I is not changing. Okay? So what you can do is you can attach a mass to a string, apply a tangential force to the mass, and its speed will increase. Okay, you'll give it a tangential acceleration. So the torque will be the force you apply times the moment arm. The torque will be the force you apply times the moment arm. But when you apply this force, you gave it a tangential acceleration m times at times r. But as the speed is increasing, it has an angular acceleration as well. So this tangential acceleration, you saw that can be given in terms of angular acceleration like that. Okay. So torque will be m times r alpha times r. Torque is and torque is mr squared times alpha. Mr squared, m times r squared is the moment of inertia of that point particle. So it's I times alpha. So here's a derivation of this law. Okay. The torque applied is equal to I times alpha. Okay. Newton's second law, where I is constant. Okay. Again, in the next chapter, you'll see that in general, torque is dl by dt, where L is the angular momentum. Okay. Okay. So then, and here was Newton's second law, when the mass does not change. Okay, the net force, when several forces are acting on an object, the net force acting on the object is mass times the acceleration of the object. Similarly, when several forces are acting, you just add up all the torques, and the net torque is I times alpha. Okay? So the net torque just means if there are several torques acting, you just add up all the torques. Okay? And again, this formula I'm just writing down. So in general, these would be vectors. Well, these would be vectors, but about a fixed axis, these are either positive or negative numbers because the torque is pointing along the axis either one way or another. Okay, so you're just adding a bunch of numbers. All right, so let's say you're pushing a cart and it's moving at a velocity v. Okay. You saw that the rate at which you're doing work, or the power, is F dot V. Okay, so for instance, if you're driving at 95 miles an hour and the engine is, you're applying a force of that, the engine power is given by that, F dot velocity. Okay. Similarly, if you have an object that is rotating, so when a motor is rotating at constant velocity, now if it was frictionless, you wouldn't have to apply any torque and it would just move. But because there is friction, you would have to apply a torque to keep it moving at a constant velocity. Okay, the power is very similar to that. Okay, force got replaced by torque, and velocity got replaced by angular velocity. Okay, so the rate at which you're doing work is the torque you applied times the angular velocity of the object. Okay. That's what this formula is telling you. Okay, so this is the work kinetic energy theorem for linear motion. Okay, so let's say initial velocity, final velocity. So let's say there were several forces acting on this object. So we'll say friction and so on, F2, F3. Okay, so if you add up the work done by all these guys, what the work kinetic energy theorem told you was the net work done was equal to the change in kinetic energy. All right, so here's a situation where here's this pulley. This weight is trying to rotate this guy counterclockwise. This weight is trying to rotate this clockwise. Okay, and you can have many other torques acting on it. Okay, so what this theorem tells you, and I'm not going to derive this, what this tells you is the work done by this torque plus the work done by this torque, okay, the net work done shows up as change in rotational kinetic energy. Okay, so that's the exact same parallel of that. So the net work done is the final rotational kinetic energy minus the initial rotational kinetic energy. Okay. All right, so this table summarizes all the formulae we have seen. So these were the formulae you saw in the first 9 chapters, and these are the corresponding formulae for rotation of a rigid object about a fixed axis in chapter 10. Okay, and again, you can go from here to there by doing the following simple replacement. X gets replaced by theta, V gets replaced by omega. A gets replaced by
Alpha.
alpha. Mass gets replaced by,
Moment of inertia.
very good. Force gets replaced by torque. Linear momentum gets replaced by angular momentum. Now, this will come in the next chapter. Okay. And that's about it. Okay. So you put the same wine in a new bottle and then charge them extra. Yeah. All right, so for every formula here, you get the corresponding formula. So for instance, here's a varying force. The work done by this varying force is this integral. And so here's a varying torque. Torque is a function of theta. Okay, so the work done by a varying torque is given by this integral. Torque as a function of theta, d theta. Okay, and so on. Here's the formula for kinetic energy, 1/2 mv square. Every point on the object is moving with the same velocity. Every point has the same angular velocity, 1/2 I omega squared. Okay, and so on. Linear momentum is mass times velocity. Angular momentum is I times omega. Okay. There is Newton's second law. Net force is dP by dt. Newton's second law. Again, net torque is dL by dt. We'll mention this again next chapter. Okay. All right, that covers the main topics from this chapter. Here's an interesting application. Okay. So here's a device that has data along this line. Okay, so the data is on that line. And the data is encoded like so. It's encoded in bumps. Okay. So ones and zeros. Okay. So that's how data is encoded. Okay. And what you're doing is, and the way you're reading that data is, there's a laser beam pointing like that, and you're looking at the reflected beam. So if you hit a bump, there's not a strong reflection. When you hit a flat spot, there's a strong reflection. Okay? So when you have a strong reflection, that's read as a 0. All right, here's the deal. So I'm pointing the laser. The laser is like this, and it moves steadily outwards. Okay. What happens is the disk is rotating under the laser, and this line has to pass at a constant rate. That data encoded has to pass at, let's say, 5 inches a second or whatever under the laser. So it's got to maintain a constant speed. So the velocity has to be constant. This has to be constant. And as you go further to read the data, as r is increasing, what has to happen? This has to decrease. So you have to have a variable speed motor to read data on there. Yeah? So that's how this thing works. So you're moving away, the laser is moving away radially at a constant rate, and to be able to read the data at constant rate, the rotational speed, angular speed, is decreasing at a constant rate. Okay. Now, okay, so a laser is pointing there. Okay. An electromagnetic wave has a wavelength. Okay. So the shortest bump you can read is roughly the size of the wavelength. Okay. So if you want to pack more and more data into this thing, what do you have to do? you have to make the size of the bump smaller. To make the size of the bump smaller, you have to use a laser whose wavelength is shorter. Okay? And blue laser has a shorter wavelength than red laser. That's what those Blu-ray technologies were. This was before you were born. I mean, this is almost a dead technology now. But CDs used red laser, Blu-rays used blue laser, obviously. Okay. And you can see that the density, linear density increased by a factor of 5. You could pack 5 times more information in the same disk. Yep.
What's like the shortest laser you can use? Because I mean, if they get too short, isn't that like gamma rays?
Yeah, you don't want to.
And you couldn't use that?
Yeah, producing gamma rays is very energy intensive. It's not worth spending that kind of money for music. What's that?
Is there like too much energy for them to do it?
And all kinds of issues, and then focusing will be an issue and all that kind of stuff. Okay. So actually, this Blu-ray has a wavelength that's 5 times. Okay. So you can see that this density groove spacing is 5 times closer, and the bump spacing can be 5 times closer as well. So actually, you can pack 25 times more information on the same disk. 25 times more information. Okay? All right, we'll stop here.